So thank you everybody for your time this afternoon. So I'm going to be talking about something that you all know I find very interesting, and that's I'm going to be talking about secondary prospectivity of critical metals in mine waste materials across Queensland. So I don't have to give any background because Rick and Blad and Helen have opened it up really nicely in terms of what we define as critical metals and new economy metals. What I'm going to, though, draw attention to is the amount of mine waste we have in Queensland. So you would have seen a number of reports over sort of the past decade or so, sort of trying to quantify the amount of mine waste material we have in Queensland. So you'll see numbers that sort of range from many thousands to a much smaller number. But in terms of significant mine waste that we have in Queensland, there's about 120 sites, which are sort of priority sites to the department. And on top of that, obviously, we have at least 40 significant mining operations, all of which are producing operational wastes, which need ongoing management. But what some sites across Queensland have shown us is that instead of, pouring money into costly rehabilitation, we can actually adopt an economic rehabilitation approach to managing this waste by actually assessing it, the metal tenor. How fertile is this material? And as the global thirst for critical metals is obviously increased, now we're looking at a whole different suite of metals that we wouldn't have considered even mining back in the day when things were first operational. So we've got this real good opportunity to actually introduce this concept of economic rehabilitation at many of these sites. And already in Queensland, we have some projects of this. So we have Century Mine, where obviously zinc's recovered. It's not defined as critical per se, but it's certainly an example of reprocessing waste and pulling out commodities and making a profitable business. And we also have an example at Mount Carbine, where again they're looking at reprocessing tailings to recover tungsten. So we have already ongoing projects across the state, but is there an opportunity to add more? And that's what I've been looking at over the past few months with the department. So in this particular project, we've gone out to a number of sites. You may have seen this slide before, and it basically just covers off on the scope of what this project's doing. So we're not looking at sort of doing a JORC resource on any of these sites. We went out and we sampled a number of sites. We did sort of geochemical assays. We've done mineralogical investigations. We've looked at mineral chemistry. We've even managed to do some intact chemical element mapping using some of our new technologies at the University of Queensland. And what we're trying to do is we're trying to look at, what's the tenor and deportment of some key critical or new economy metals in these materials. And if we can find something interesting, then, it's worth going back to these sites and actually undertaking a more detailed investigation. So this is our phase 1 investigation. So in this small amount of time, and believe me, I found this very hard to put together because there's so much to say, and I know that I've got to keep it brief. But if you want to have some more information on what we've done, we'll be releasing an interim report on this work very shortly. So moving on, the particular sites that we were sampling are listed here. So you can see we've got Capricorn Copper, Lady Annie, Century, Osborne, Selwyn, Wolfram Camp, Baal Gammon, Mount Oxide and Pindora, several of which you heard about in Vlad's talk previously. So in terms of waste types we were targeting, we sampled things ranging from waste rock materials to tailings to heap leach materials. And in terms of the commodities we were looking for, the target elements, we looked at cobalt, we looked at indium, we looked at tungsten and gallium and germanium. So those are kind of our main focuses. But of course, the list of new economy metals is quite long. So as we drill down on some of the final chemical data sets, we'll actually be looking at a lot more than what we've just specified there. But for the sake of today, that's what I'll focus on. I don't have time to talk about the geology of any of these deposits, but just if you are interested in learning a bit more, then obviously we have the Deposit Atlas series, which you've heard about in previous talks. So that's somewhere to go. And in terms of where we sit in this project, obviously we started back in November, went out to do our sampling in sort of February, obviously weather permitting. There was a few issues with getting to some of the sites. And, reasonably speaking, we haven't been too affected by COVID in terms of undertaking our characterisation work. So the last lot of samples have got down to codes at the University of Tasmania for the laser ablation work, and the XRD results are soon to be finalised. So we're tracking well, and we're looking at producing the final report in June. which I think is going to be a big piece of work, looking at the number of sites that we've tackled in this project. So the first one that I want to talk about is Capricorn Copper. So you may have seen this slide a couple of weeks ago when I last spoke in one of these forums. Here we had the opportunity to sample the tailings. So you're looking at the Esperanza tailings there. We also had an opportunity to sample some of the waste rock. I should probably have put the laser pointer on, but if you can see my mouse, then you've got the waste rock all to the east of the site here. So we were able to access some of the tailings at sort of about up to 1 metre depth on the day using UETEC sampler. Because we had gone out to sample after a big bout of rain, we were unable to get down past that. You're going to see why that's significant in a few slides' time. So we did manage to get a decent coverage, and because obviously it was summer, some of the water cover here had sort of receded, so we were able to access some of these areas which are normally subaqueous. So in terms of what we saw, with the tailings, we identified about 6 different tailings species. They were quite distinctively different. If you have a look at this core photo here, so this is one of the sediment cores that we obtained from the UETEC. Broadly speaking, what you can see is there's obviously an oxide, an intensely weathered crust at the top of the core, and that grades slowly into this more sulfidic material. And the sulfidic material is important here because it's here where our cobalt grade starts to go up. So if we look at the distribution of cobalt across the dam, plotted in IAGAS and married up with Google Earth, we can see that it was quite lucky and fortunate that we were able to sample in the subaqueous zone, because here we start to see some of the higher cobalt values. So if we were going to go back and do some more sampling, then perhaps getting out on the boat and actually obtaining some of the cores from depth would probably be quite sensible in this particular area. And in the subaerial zone towards the south of the site, we can see we had slightly lower cobalt numbers down there. And in terms of copper, again, we saw slightly higher cobalt numbers in the northern portion of the dam. But we occasionally saw these hot spots of high copper, and that's sort of related to the formation of salts. So obviously, this is a very, occasionally very warm, I say that in a very British way, it's a very warm climate, particularly in the summer, as I found when I melted. But that obviously induces the formation of soluble secondary efflorescences. And if you sample those, they actually concentrate quite a lot of the mobile metals in this environment. So we did find localized hotspots of copper. And if we flick over to the waste rock, what we can see here is quite a different story. So I've pulled out a couple of examples of high cobalt waste rock samples, and you can see these don't look particularly sulfidic at all. And in fact, what we found here is that our cobalt is more hosted and associated with iron oxides. So if we just have a quick snapshot of the different elements and the different waste types and start pulling out some key relationships, we can see that now if we plot cobalt against sulfur, we can see that cobalt's most likely hosted in sulfides. But if we look at the waste rock, it definitely doesn't look like it's hosted in any sulfides there. But instead, it looks far more likely that in waste rock materials, we have cobalt hosted in iron manganese oxides. And this was a common signature across all of the sites that we sampled. Cobalt and nickel, as we would expect, showed very strong positive correlation. And occasionally, looking at the relationship between cobalt and copper, we could see there was, in both waste types, particularly strong in the tailings, there did look to be a bit of a co-relationship there. And so we did some MLA mineralogy on just high cobalt samples. Looking at the tailings specifically, we can see a dominance of sulfides here. So we had about up to 8.8 weight% pyrrhotite and 4.9 weight% pyrrhotite, and sort of minor sort of chalcopyrite and bornite. We also did have some iron oxides, and if we look at the waste rock material, we can see it's quite a different story. So here, again, very much dominated by iron oxides, and these iron oxide silicate intergrowth phases. Very minimal in the way of sulfides here, which is consistent with our field investigations. So when we were scratching around the waste rock piles, it's very hard to find any sulfides, and that's obviously evident why. But one thing that we did see in quite high abundance was manganese oxides, and actually one of the minerals that we pulled out here was asbolane, which is a potential host for both cobalt and nickel. So we're going to be undertaking some laser ablation work to investigate the chemistry of these phases a bit further. So moving on to site number 2, Lady Annie. So again, it was another fantastic opportunity to sample 2 waste types at this site. So we managed to get a good section of bench 1 and bench 3 on the waste rock pile. So we sampled from pads 2 to 14 here. And over at the waste rock pile, we were able to sample waste rock materials of slightly different ages and generations. So we had a slightly newer pile, I should say, or fresher pile, and some older material there. So, and we saw that obviously in the materials that we encountered, where we saw this sort of massive kind of chalcopyrite, which is sort of more proximal to the transition zone. And in older parts of the dump, we actually saw more like copper carbonates and so forth precipitating out. So in terms of locations of cobalt here, what we can see is the highest cobalt concentrations were measured in bench 3, so in the younger, fresher material. And if we look at the heap leach chemistry and mineralogy down here, we can see we had a maximum cobalt concentration here of about 129 ppm, which is, I suppose, for heap leach materials, pretty high actually. So in terms of the MLA mineralogy for the high cobalt samples only, we can see here that we have a likely host of iron oxides because the rest of the mineralogy is pretty much silicate dominated. Now, if we flick over to the waste rock material, what we can see here is that we had a maximum concentration of 335 ppm in this particular sample here. And what we can see here in terms of the mineralogy, again, we've got a lot of carbonates now coming through, again, silicates. But, we also had identification of pyrite in these materials, so it's potential that some of the cobalt here is located in that particular mineral group. And if we look at copper across the site, obviously, I'm sure everyone's interested in copper because it's a copper operation. So there's a couple of hotspots of copper towards the centre of bench 3 and also down here at this at the toe of this bench 1. And if we look at the heap leach concentrations of copper, see a maximum of 12,400 ppm. So the average ore grade here, if we look at the sort of mean and the median, it's at 0.6% copper. So I think what this is saying to us is there's opportunities for additional copper recovery from these pads. And if we look at the waste rock material, again, as we would have expected from some of the pictures that I showed you earlier, cobalt is pretty choppers in the waste rock, so maximum of over 100,000 ppm. We saw many examples of chalcopyrite, and we saw copper carbonates and chrysocolla and all sorts of things in these waste rock materials. So in terms of winning some more copper, there's some opportunities there. If we flick over to Mount Oxide, this was a site that had, probably about 2011, 2012, KCB undertook a big project here where they looked at drilling cores through the piles, and they did some portable XRF that are mostly focusing on defining the static or the acid-basic counting type properties of the materials. So in terms of like undertaking full assays or detailed assays to look at some of the elements that we're interested in this project, wasn't quite available. Whilst they have done portable XRF, as we're all well aware that portable XRF information, particularly for cobalt, isn't always that reliable. So I haven't shared these results in this presentation today. I've stuck to our assay geochem. So on our particular sampling day, we went across the site and we collected 40 different particles from the surface and thereabouts. So here's an example of some of the things we found. So in terms of cobalt, maximum cobalt concentration we recorded was 391 ppm with an average of about 134. Certainly definitely a concentration of cobalt-rich samples in this particular area towards the centre of the site. And if we look at sort of the types of rocks where we found high cobalt values, we can see that they're in these very limonite, sort of iron oxide-rich samples and very kind of sooty hematite and magnetite. And if we look at the copper, what we can see again, really, really high hotspots of copper across this site, up to 500,000 ppm. And we can see here in terms of copper mineralization, you can see again lots of examples of copper carbonates and chrysocolla and some other copper sulfates. So if we look at the MLA mineralogy for just some high cobalt samples, we can see, it sort of confirms our site observations and our field observations in terms of the fact that these are not sulfidic materials. They are very complicated in terms of their iron oxide chemistry. So when we were doing our MLA work, we've got things here like iron oxide, high BSE and low BSE. So we can see we've got a lot of magnetite, hematite, potentially hosting that cobalt. So the plan with this particular site would be to do a lot more detailed laser ablation work to work out which iron oxide phase is the most endowed in terms of cobalt concentrations. Moving on to Pindora. So here, this is a small site towards the east of the Kalman deposit. Not too much information out there, I must say, in terms of the history of this deposit, but it did operate as a predominantly copper operation. Here, what we are looking at is a heap leach pile. So this heap leach pile is probably about 5,000 cubic meters of material. And we also were able to sample a small waste rock pile to the west of the heap leach pile. So here's an example of one of the transects. What we did at this heap leach pile, where we could, because you have to appreciate this is on an incline and we have to think about health and safety, we tried to do a few vertical transects along the pile just to get a sense of, I guess, a time-wise sequence in terms of the changes and variations in new economy metal concentrations. And here's an example of the pile, the mullet pile, I suppose I should call it, looking back towards the main heap leach pile. So you can see here, again, there's a lot of chrysocolla, carbonates and so forth precipitating out on the surface there. So in terms of cobalt concentration, what we can see here is that in the heap leach material, we had a maximum of 342 ppm with a mean of 148. But it's really the waste rock where we saw the highest cobalt values. We had a maximum there of 415 ppm. And if we look at the MLA mineralogy of some of the high cobalt samples, we can see for the heap leach material, much like at Lady Annie, the iron oxides are our target phase for further investigation. And the same thing again here for the waste rock mineralogy of the high cobalt samples. So the waste rock in terms of sulfide mineralogy was, for the high cobalt samples, I must specify, basically looking at an iron oxide host there. And if we look at the copper concentrations at this site too, again, we see it's really high, so up to 9.82% in the heap leach material, up to 11.3% in the waste rock material. So, you know, there's a lot of more work to be done in terms of looking at the iron oxide chemistry at this particular site. Now, flicking over to a completely different commodity, we're going to take you to Baal Gammon now. You heard a bit about Baal Gammon from Vlad. So what we're looking at here is this, obviously quite a bright graphic, but we're looking at a PAF cell. So this is basically the main dump. And here what occurred was that all of the acid-forming material was placed into this potentially acid-forming cell. Subsequently, a plastic liner was placed over the top of the dump to kind of restrict the formation of acid mine drainage, which is sort of eluting off to the Jamie Creek and so forth, Water River, I think. But as time's passed, we can see that the cover's actually degraded, which is obviously not great for the site, but in terms of our sampling, it provided us a really great opportunity to get some samples under the cover, because at Mount Oxide, I don't know if you would have noticed, but some of the stockpiles were covered in some really thick plastic, so we couldn't sample those. That's sort of another thing that influenced our choices of sampling there. So this did give us an insight to go and have a good look around the site and obtain some really tasty samples. Very tasty samples they were indeed. So what we, unfortunately I can't show all of the images, but if you download the report, you can see them all in the appendices. We had these beautiful polysulfidic materials, arsenopyrite, chalcopyrite, pyrrhotite, sort of really complexly, I guess, intergrown with each other. And you could tell which ones they were because, as we can all appreciate, really thick oxidized grinds around them. And then when you pick them up, they were super heavy. So, you know, it was easy to get distracted at this site with shiny sulfides, but obviously had to keep focus at the target. What we were looking at here was indium. So we wanted to have a look at sort of finding some good samples so that we could do some good indium mineralogy and geochemistry work. So in terms of concentrations across the site, as I've said, very polysulfidic site. So we actually had quite high cobalt here, which was a surprise. The cobalt here is hosted in arsenopyrite. And, you know, again, appreciably got arsenopyrite and chalcopyrite, so these values were also quite high. In terms of indium, we had a few, probably about 3 or 4 samples, which were measured in terms of assay values greater than 500 ppm, as you can see on this distribution graph, or map, I should say. And when we looked at the waste rock mineralogy of the high Indian samples, what we saw was, as we would expect, a lot of sulfides, pyrrhotite, chalcopyrite, arsenopyrite, and some of the other silicates that are common to this area. So our hypothesis and what we know about this site from previous work, looking at sort of fallen waste boulders into the Jamie Creek, is that the Indians predominantly associated with chalcopyrite and sphalerite as inclusions. So that's kind of where we need to go in terms of focusing our laser ablation work. So we need to actually work out, is the Indian solid solution, or is it present as rocasite, or, yeah, so that's a tricky thing to do with laser ablation. So we're working with the team down there to do that properly. Had to put this in. So you saw a few weeks ago Rick showing some of his element maps from his favourite rocks, and this is an example of some chemical mapping we did on the same instrument here at UQ. This just gives you an idea of the sort of complex sulfide textures we're working with, and it's important to actually have maps like this because they start focusing your mind in terms of how you would undertake mineral processing. So, you know, chalcopyrite potentially is, in this particular sample, the host of indium. So we need to think very carefully about how we would recover that chalcopyrite. So flotation obviously would be a great tool to use. So I guess it's about designing the appropriate recovery program. So, you know, as much as we get focused sometimes as geoscientists on sort of the very micro scale, it's important that when we're thinking about reprocessing these materials, we need to also think about macro scale features and how amenable they are to processing. So I just wanted to highlight that. Okay, so we also heard about Wolfram Camp. This is a site that's been looked at by two groups of researchers at the SMI. So thankfully I'm involved in both. So you'll see reference here to this study and the Adraki study. So Ansel Adraki is a colleague in the Centre for Mine Land Rehabilitation at the SMI. So they went out in October 2019 and did some sampling in some of the tailings material here towards the north of the site, which you can see on the Google Earth map. What we did was basically some infill sampling. So what they hadn't really targeted too much was the low-grade ore and the waste rock materials. So we took some material here from the Parrot Pit, and we also sampled some of the PAF dumps and the waste rock piles here. So here's an example of a view of some of the tailings here. And some of the features we saw in the waste rocks, saw this kind of really grotty, clotted sulfides occasionally. And we also saw lots and lots of molybdenite at this site. So there were flecks of moly everywhere. So if you're wondering what that is, that's my gloved hand that moly fleck is sitting in. And here's an example of obviously just the site here. So in terms of the chemical and mineralogical summary, it is log scale low. So when you look at those average values, you have to consider that. And that was the same thing that Adraki found in his study. So where they did sample some of the waste rock material, they also found that that was more endowed in tungsten than the tailings. In terms of moly, well, you know, that was choppers all over the site, molybdenite. So one thing that's interesting, you know, Vlad made the point very clearly about rhenium being a new economy metal, and that's something that we're going to be looking at a bit further at this site. So the bulk sort of assay data didn't sort of suggest that the rhenium was particularly high, but we do know that if we investigate the chemistry a bit further with laser ablation, we might have something to add to that. In terms of the waste rock mineralogy of the high tungsten samples, we can see, you know, this is pretty much hosted in wolframite. Looking at calcium values and other things, and obviously the MLA mineralogy, there's an absence of scheolite. And the same thing again we saw in the tailings mineralogy. Okay, moving on to Osborne and Selwyn TSFs. So we were fortunate that Chernobyl very kindly provided us with some information on their samples for these two particular sites, both of which from their assay work show sort of preliminary high grades of cobalt in both their tailings storage facilities, so 856 ppm and 582 ppm. And for Selwyn, again, we're looking at about 114 ppm from their preliminary work that they've done assaying around there. So what we did was basically look at the MLA mineralogy of some high cobalt samples. So we took a list of their samples and we cherry-picked kind of the highest cobalt samples. Because what we wanted to know here is the cobalt just hosted in sulfides, or is there a component of cobalt potentially being in magnetite too? So that's what we did at both sites. When we looked at the MLA mineralogy, what we found, again, obviously there was a high abundance of iron oxides and both iron sulfides, particularly at Osborne. And at Selwyn, we found that sort of a bit more of a dominance of plagioclase and actinolite and a lower content of iron sulfides, which perhaps is reflected in the cobalt grades that have been preliminary calculated. So if we look at some laser ablation data, and this is hot off the press, so I haven't been able to dig through it in a great amount of detail before now, but as a summary, what we can see is that in the pyrite, we have up to 80,000 ppm of cobalt, which is pretty high, with a high average grade of just over 10,000 ppm. For both sites, pyrite is the most endowed in cobalt. And that's followed by pyrrhotite again for both sites, and then that's followed by magnetite, where there's a significant kind of order of magnitude decrease of the content there. And so if we look at cobalt in pyrite and how it's actually deported, we can see that in pyrite, it appears to be lattice bound and associated with nickel, which is consistent with something that I said earlier about cobalt and nickel in all of these sites appearing to couple, which is what we'd expect. And not that you can see it here, but we saw occasional chaff pyrite or copper microinclusions in these signatures. And again, looking at cobalt in magnetite, we see the same thing again. Cobalt's lattice bound, it's associated with vanadium and manganese, particularly in Selwyn. So just to get to the last few slides, I guess our minds are always going to be turned into a comparison of sites. Where should I go and have a look? What's tasty? What's a bit less tasty? So this is kind of a summary of that. So the Osborne tailings, as you can appreciate from looking at some of the numbers there, it's obviously the most well assayed and it's the most studied of the sites, but it, you know, based on the calculations that they've undertaken, it's definitely got the highest cobalt. And from the laser ablation study, what we can see is it's refractory in pyrite. So again, when we're starting to think about recovery options in terms of metallurgical options, potentially suitable to bioleaching. Bioleaching has become something that's gained a lot of interest over the past 10 years, particularly for cobalt recovery. I mean, there's a lot of literature around using bioleaching technology in both sulfides and oxides to recover cobalt. So that could be a potential option there, and also for Selwyn too. Now, the next tastiest site to go and have a bit more of a pour over is probably the Capricorn Copper waste rock dump. So there's manganese and iron oxides. You know, particular manganese oxides, there's something very interesting going on there. So in terms of having a bit more of a detailed sampling strategy and a bit more detailed characterization, that could be a place to go and have a look at. Followed actually by Pindora. So I was actually quite surprised by the cobalt grade in the waste rock material that we sampled there. Yeah, granted, it, you know, in future campaigns we probably would do a lot more extensive sampling, but it does give the impression that of all of those collections of deposits around there, it's definitely worth targeting any mullock dumps or waste dumps in that area, and perhaps, you know, concentrating them into one new operation, who knows. And that's followed by the man oxide waste rock. So thinking about Lady Annie, you know, the waste rock, yeah, yes, there was cobalt there, and it's predominantly contained in both sulfides. But if we look at the heap leach materials at Lady Annie and Pindora, they were both less endowed than the waste rock sampled at those sites. So in terms of going back and thinking about cobalt recovery, it's possible. Is it profitable? Maybe not. Maybe we'll have to do more work to determine that. In terms of how you'd recover it, as I said, there's been new studies looking at how you would pull out cobalt from iron oxide material of this particular nature. So that's something to potentially consider as a metallurgical option. And the lowest values of cobalt that we came across was actually, annoyingly, because I thought it would be the highest when I first set out on this project, was the Capricorn copper tailings. But as I say, I'm stressing that this is in the sampled materials only. So we only managed to sample in the upper meter. If we'd have got much further down into much more of the sulfidic material, I think that we would find that the tenor of cobalt would significantly increase. So it's definitely on my list of things to do in the subsequent projects. So just going to finish on what's happening next. So this project's going to wrap up in June, and all of that data, this is a data dense project, I hope you can appreciate, will be brought together and summarised. And then we'll be kicking off project 2. But again, we're going to be focusing on investigating a lot of different sites across Queensland. We're going to cherry pick a couple to do some detailed site investigations, but we really do get to grips with the sites, the mineralogical hosts and the sites, and the various mineral chemistries of where these new economy metals are sited. And then we're going to look at sort of some appropriate mineral processing methodologies to recover these. So there's lots of options on the table. I've mentioned bioleaching, but that's not the only new one that's come to the table. So we're going to be looking at all of these and thinking about what we could do differently to economically rehabilitate more sites across the state. So on that, I should say no more, except for thank you to Helen. And thank you to a long list of people who've made this project possible, from both GSQ, SMI, the mine sites, collaborators in other universities and so forth. So thank you, everybody. Thanks.
Thanks, Anita. So we're now a little bit behind, but there's a stream of questions here for Anita. I do have one comment that could all questions appear in the Q&A rather than just the questions being answered. So some of the questions have gone into chat, which is fine, but just make sure that you select all panellists and attendees, not just the panellists, so that everybody else can see them as well. We might just move through very quickly the questions, because I know a lot of people will be interested. Anita, your study shows there is a high concentration of one new economy mineral in some mine waste tailings around the dam. Do you report the assay results to the owner of the mine and let them develop, or do you pass on to the GSQ for geoscientific study, or is this research work only?
I guess the intention right now is that we're passing the data back to GSQ, and all data that we've collected will be reported to the mine owners. So I guess it's kind of a bit of everything, really, if that's a way that I could answer that.
Yeah, I guess from the GSQ perspective, any research that we fund is meant to be publicly available. So our job is to promote mineral exploration in the state, so that as our funding of Anita's work, therefore the ultimate goal is that it's all public.
Yep.
Joe Potter is asking, what is the pathway to commercialisation of tailing sites which are shown to contain critical minerals of interest? That's a complicated question.
Good question. I guess what we're doing is we're just demonstrating the fertility or the location of some of these metals in these materials, and looking at how they could be recovered metallurgically, and that's information that we're going to report back to the GSQ and to the sites. In terms of pathways to commercialisation, that's something that we'd have to, I guess, then discuss with the companies and with sort of some of the METS companies in the state. There's a lot more that needs to happen. I mean, we haven't exactly sampled at this point for anything that's JORC compliant, so that would have to be the first thing that we do. Yep.
And was consideration given to looking at Mount Cobalt, as it was the only actual cobalt sulfide producer in the belt? From Simon Beans.
Yeah, fair question. We basically organised this project reasonably quickly, so we had to get permissions from people also reasonably quickly. So in the next phase of the project, we're going to go back and do a lot more sites in this manner. So there's every opportunity for us to work with Mount Cobalt then, but we just couldn't get them into the first phase. Yeah.
And one more question, Anita, before we quickly hand over to Kate. The indium in the copper, and I think this is following on from Vlad's talk, but we've got you now. So, the indium in the copper tin deposits, how accessible is it? Is it a refractory mineralogy? Yambo Chang has actually answered that question. It was, but only to all panellists. So I will read out his answer. Indium in the tin copper systems globally, the major hosting minerals are sphalerite, cassiterite, chalcopyrite, sometimes stannite.
Yep. Agree with that. Yep.
All right.